Hello and welcome back. In this video, we discuss about Reynolds transport theorem, an important concept in fluid dynamics. In the previous video, we discussed about the concepts, system and control volume. By definition, a system refers to collection of matter of fixed identity, which may move, flow and interact with the surroundings. For example, a finite amount of fluid flowing through a pipe is a system. On the other hand, a control volume refers to volume in space, through which fluid may flow. The volume is purely a geometrical entity, and it is independent of mass. The control volume can be fixed in an appropriate space, for convenient analysis of flow. Consider another example of a jet engine. The possible streamline patterns of airflow into the engine is shown in figure. In this example, the finite quantity of air flows into the engine is a system. To study the dynamic interactions of this system with the engine, an appropriate control volume can be chosen as shown in the figure. Note that the system crosses the boundary of control volume, called control surface, at two places. Consider another example of a system and control volume. Air is flowing out from a small opening of a compressed air tank. We can consider the compressed air as a system with constant mass. To study the dynamics of this system, we can imagine a control volume fixed inside the tank, as shown in figure. In this case, the mass inside the control volume is constant initially. As time passes, the mass within the control volume decreases. When a system moves through a control volume, its extensive properties may change. For example, a change in momentum of a fluid system causes reactive forces on the control volume. In this video, we discuss about Reynolds transport theorem that relates changes in extensive properties of a system to its changes inside and across a control volume. The goal is to derive appropriate mathematical relations that can be used for fluid dynamic analysis of a given flow system. In a control volume analysis, we focus our attention onto the control volume and observe the motion of system through it. In many practical cases, the reactive force developed by moving system on the control volume is of interest. Mathematically, we can show that rate of change of an extensive property of a system is equal to the rate of change of its intensive value integrated over the control volume, plus its net flow over the control surface. This is called Reynolds transport theorem. We will discuss the meaning of each term one by one. dB system by dt is rate of change of an extensive property of a system. For example, it can be rate of change of mass or momentum of the system. In the next term, small letter b is the intensive value of property B under consideration. Meaning of these terms can be discussed next. Raw dV is differential mass of the system within the control volume. B, raw dV is value of intensive property for a differential mass of the system within the control volume. Finally, the second term refers to the rate of change of value of intensive property for a differential mass of the system within the control volume, integrated over the entire control volume. V.n is essentially the projected velocity of fluid particle to the normal vector of a differential area. This is velocity component normal to the differential area. Raw times V.n dA is mass flow rate through the area dA. Note that, if vector n and velocity v are orthogonal, no mass is crossing this area. Finally, when multiplying mass flow rate with intensive value of system property and integrate over the entire surface, we see that the final term corresponds to net flow of extensive property into the control volume through the control surfaces. Finally, let us review the Reynolds transport theorem. The rate of change of an extensive property of a system is equal to the rate of change of its intensive value integrated over the control volume, plus its net flow over the control surface. The extensive properties of system can be its mass, momentum and energy. In the next video we will discuss the principle of conservation of mass using this theorem applicable to fluid flow. Thank you for listening.